Well, hello. My name is Muhammad Zafar Bismanov. My topic is modeling of evapotranspiration in different types of soils and crops. I thank Dr. Theo Espinosa and Chris Henry for their support and contribution. You know, the water management is a big issue today because of weather problem, drought, dropping of underground water level. So we have to develop our irrigation schedule to save the water resources and achieve the good results. How we can do this? If you remember, maybe among you, 5-6 years ago, I thought that ET irrigation scheduling is the best for large farming. In that time, I showed some correlations between the soil moisture and ET. So look at this today. Many states now developing their online irrigation scheduling and smartphone applications on the basis of this method. Of course, we are working hard on soil moisture sensor based on irrigation tools, but in fact that today they are expensive and needed more specialists. My message today is when we use the irrigation scheduling on the basis of ET, we have to be very careful, because not always the ET data can compare the calculations to be present the field data. It's avoided. That's why we have to develop our modeling and the research on shrink this gap between the field data and our data from ET methods. Let's look deeply on what ET is. If we know the yearly precipitation in the earth, how much, and then how much energy we need for vaporization 1 pound of water, we can calculate how much energy we need for supply whole earth with the precipitation. It's 32% from all solar energy we receive. It's true because ET is very important for our lives. We're feeling it in our body. ET gives us temperature balance for our bodies. Same thing with the earth. Look at the Sahara desert, hot because of no water, no ET. And then more importantly, moisture and nutrition movement in the soil due to ET. I give the idea that if you control this one in the soil, you can control the whole agriculture. How we can measure ET? By standard evaporation pan, ET gauge, atmometers, weather stations, and lysimeters help us to measure soil and plant evapotranspiration. But they have lack. They are isolated from main system of the earth. I dig up. I can tell you that in the vegetation period, the 5 feet deeper soil gives its moisture to the plant. The second thing, that lysimeter is very expensive. We cannot multiply our experiment. So that's why I developed double bucket container system. I increased unto 48 system and put the different type of soils and crops, and we have a lot of data on that. If you look at PET trends, all devices are all almost the same, just little difference because of different principle of work. Morning evaporation less than afternoon evaporation. We know that night evaporation almost zero. And what about the soil evaporation? Soil water evaporation is different. Some type of soils like sand soil can give more evaporation in the morning hours, but the clay soil always gives less evaporation. Give me the idea we should look at more deeply to this process. And I designed the experiment that includes the different type of soils, and in the middle I put the cup with the port in the bottom, and I put the graduated cylinders with the water, and the next to the tray I put with the water to compare with water surface evaporation with soil evaporation. And after 2 hours, you can see that in sandy soils, we have the spot. After 12 hours, we have the moisture in all the soils. Look at the process. It's very interesting. It looks like the living creature, the soil, drains the water with different way, different water types. It's very interesting experiment, and look at the results. In the beginning hours, the sandy soil have more water penetration than other soils, up to 4 times more. And after 8 hours, the other soils take the more penetration because the sandy soil's water is penetrated already in this soil, and after 24 hours, everything stabilizes, and after that is going the evaporation process. So if you look at the evaporation, we can see that the soil evaporation is more intensive than water evaporation here. I put the atmometer graph to compare. You see the water surface evaporation, atmometer evaporation almost the same. So what about the cumulative evaporation? The sandy soil give 1.4, 1.5 times more than water surface evaporation. And then clay soil just 1.1. So how we can explain this? I try to explain with the modeling of soil. You know, the soils differ with size rather than shapes. The average shape of the particles is sphere. So I take the sphere, you see the clay particle very small as the earth against the sun, right? If you put the all together as much as we can, even so we have the vacuum between the uniform particles. It's 30% of vacuum. This means you can say that the geometric water capacity of this model is 30%. If the different size of particles, this vacuum shrinks until 9%. It's close to the sandy soil characteristics. I developed this model and put the different combinations. You can see the graph, the water capacity changes from lower to higher, from sandy soil to clay soil. And this is very close to the actual data. So the model on this way is working well. Now look at the surface of all particles in certain volume depend on size. If size smaller, the surface is bigger. This means that if we take the water thickness in wilting point and apply the concept to other sizes, we have the graph that shows the water content wilting point in different soils. So this is also very close to the actual data. Now the unique video I show you, I took this video under the microscope, how the moisture moves. Look at the graph. The moisture, this is a moisture movement in the soil, not water. But in the micro wall, it looks like the flooding is going on. It looks like the earthquake, right? So this is a very interesting process. We said that just soil movement. In reality, is a big changing in the structure of soil. And on the top, you can see not flat water, just water film has some shape. On this base, I model of evaporation, spherical water film surface on the soil particles increase the air-water contact area and in the same square space than that flat surface. Solar energy absorbing increase in the darker spherical surface of the soil particles. And then, very importantly, convection increase because of different temperature here on the top and then here on the bottom, the different temperature. And here's the ratio between the flat water surface and the spherical surface of the water film. I recommend that this coefficient should be used in our calculations by energy water balance or Penman-Monte's equation. Here you see how changes the ratio from 1 close to the clay soil until 1.7, 1.6 onto the sandy soil. So this means this data, this exactly shows what we have is happening. We can see in the field these causes. For example, here you see the white spots on the row. This means the nutrition, the minerals come because of water that moves from higher hydraulic zone to lower hydraulic zone. And then we can see cracks along the row because the force direct to the middle of the row. But in usual without row, it's just uniform cracks. Also, we find out this affect to distribution of nutrition. It's very important for us. You see here the potassium and nitrogen distribution trends in drip and furrow irrigation systems, and then drip irrigation water and furrow irrigation water makes a totally different distribution of the nutrition in the row. It's very important in the future. We can use it in our results. Here the cotton plant leaf square we count the average cotton plant, for example, leaf square 4.1 square feet, and from this we can find a ratio between field plant square and leaf square 4.7. This means that the potential ET of plants may 4.7 times higher than bare soil. And then here's the model. You can see these numbers close. We find the 3.9 higher plant evapotranspiration than soil evaporation. This shows that average, the ratio 3.1. And then very interesting that water transpiration in different plants is different. It's interesting in the morning higher transpiration than afternoon. And then very importantly, a correlation between leaf and cotton ball weight shows the evaporation effect to cotton ball size. And this in big scale, we can see the cotton yield depend on PET. So if we know PET, we can forecast our yield. We are developing this, so we have a lot of data, so we can work with you. This is my name, email address, contact with me on this issue. Thank you.
Thank you very much, Dr. Usmanov.